because they wouldn't want you to start off on a difficult start. So just by looking at the first part, sometimes it can be quite deceiving whether you can get a good decent score for the whole question or not. Yeah, so you gotta think carefully and very quickly. There's decision making. Yeah, anyway, it will change once you are in the exam setting, I'm sure. Okay, so they want you to use the information in the table. Predict the physical state of nitrogen at minus 200. So you need to look at melting point and boiling point. Okay, so nitrogen melts at minus 210. So if I have that temperature line diagram, so 210 degrees Celsius is going to be the melting point, and then boiling point is minus 196. All right, so you know the negative value, it increases that way. Yeah, so this is actually a higher value than this. All right, because it's a negative. All right, and you want to talk about at minus 200. So where are you at minus 200? You are going to be here at around, well, this is not drawn to scale. Melting point is solid, goes to liquid here. So all the way there, it is still a liquid. Only after it reached the boiling point, it become a gas. So it is still a liquid. N2 is I know it's N2 because it's simple molecular, whether it's solid, liquid or gas. Nitrogen, oxygen, chlorine, hydrogen. So those are simple molecular structures that exist as diatomic molecules, whether they are solid, liquid or gas. Yeah, I'm sure you know that. All right, at minus 200 degrees Celsius, and when you need to explain it, at the temperature minus 200 degrees Celsius is higher than the melting point. So meaning to say, then its melting point. That means to say it's already melted. Okay, but it's lower than its boiling point. That means it hasn't boiled. So it already melted, but it hasn't boiled. So that means it must be a liquid. I hope that makes sense, right? So you got to compare the melting and the boiling point. Yeah? Predict the melting point of arsenic. So they want the melting point, right? So you have a look here, it increased, and then here you see it decreased. So now you have a dilemma, right? Because you expect from that increase, you expect it will go higher, but somehow it decreased from there to there. So it's quite hard to think, will it be decreased or will it be increased by looking at these two? However, if I'm to decide this in an exam, what I would do really is I will follow the earlier trend. So meaning to say, I would assume it continued to increase, because then that will mean that it will continue to increase there as well. So meaning to say, there is the more consistent trend for most of them. Until here, then there is an inconsistent trend there. But that is down there. As long as it doesn't affect there, I can assume it will be okay. And it's a prediction. So you can only do a prediction, yeah? So it has to be somewhere in between. If I am to guess maybe 300, 400 or 200, they'll be okay. As long as it's not 45. 45 is too close to that. Maybe 600 is also not a good value because it's too close to that. So like 300, 200, 300, 400, 500, I think that would be sensible really, okay? But anyway, I'll just put down 400, which is somewhere in between. Don't forget your unit, melting point and boiling point, the unit is degrees Celsius, yeah? Now, you need to use information, all right? How the structure and bonding in nitrogen differ from bismuth, okay? So look at bismuth. Bismuth has high melting and boiling point. In fact, particularly high boiling point. Nitrogen, we're talking about negative value, very low melting point and boiling point. 271 is not very high, but it's still much higher than, let's say, room temperature, which is 25 degrees Celsius, right? But you can tell the boiling point is exceptionally high, yeah? Okay, so what can we say? Using the information from the table, N2 has a very low melting point, and okay, maybe I should use full sentence. Melting and boiling point, whereas bismuth So we don't know the structure of bismuth, so I just write bismuth really, okay? I mean, I don't know the molecular formula. It's not diatomic, definitely, okay? Whereas bismuth has very high melting and boiling point. Okay, now we're going to talk about the structure. All right, so I've used the data then. Okay, N2 has simple molecular structure. Okay, it has covalent bond between the nitrogen triple bond. I did mention it earlier. That's why nitrogen in the air is unreactive. It does not support combustion because you will need to break this triple bond, which is very strong. Nitrogen has very low melting and boiling point. Because of its simple molecular structure, you do not break this covalent bond when you melt or when you boil nitrogen. So what you do is the melting and boiling nitrogen, which has simple molecular structure, it depends on the structure, yeah, only breaks the weak intermolecular forces. Weak intermolecular forces between the molecules. So intermolecular forces mean between. So intermolecular, between the molecules. All right. What can you say about bismuth, because we are comparing, right? So the very high melting and boiling point means it must have giant structure. Now, do I know whether it's giant metallic, giant molecular, or giant ionic? Well, I can tell you, giant ionic, you can cancel it out because it's an element. It's an element, so it cannot have a giant ionic, all right? And then when you go down this group, there's something to do with metallic properties, which I will not address. But in general, you can talk about the group 5 elements. They are considered non-metal already. So in general, you can actually cross out giant metallic as well, all right? But I can tell you it can be giant molecular structure. So that means the melting and boiling requires breaking many strong. So we are comparing, yeah, so weak intermolecular forces versus many strong covalent bonds. That needs to be broken for your melting and boiling. That's why very high melting and boiling, yeah. Antimony, there's the symbol there. So they even give you the symbols, don't make that mistake. Reacts to chlorine. So chlorine is diatomic. How do I know that? I also don't know, okay? It's a case study. And I'm sure you have done question 1 before you reach them. Chlorine has diatomic molecules. So it's quite strange how a concept earlier tested actually comes out again and again, right, in the whole question paper. So sometimes you gotta think whether Cambridge is actually making things too easy for you or not, right? Antimony 3 chloride, so Cl minus, antimony 3 plus, you can think of it like that, even though it might not be ionic. So you need 3 chloride in order to balance out the charge of the plus 3. When you think the LCM of 3 and 1 is just 3. So you need 3 chloride there, so it's SbCl3. Here's where I'm going to go back to my half equation again. I mean the use of half, the use of fractions, right? 1 antimony is fine. 3 chlorine atoms altogether. There's 2 there. In order to get 3 over 2. 3 over 2 times 2, because there's 2 chlorine in one molecule. There's 1 and 1, there's 3. Of course, you can multiply the whole thing by 2. You get 2, 3, and 2. Perfectly correct as well, yeah? Now, they want you to use the information in the table to suggest, so it's a prediction, the density of selenium. So here you can see it increase from oxygen to sulfur. Here you see it increase again. So just by looking at the trend, you can see that the density actually increased. So you could suggest a value somewhere in between. Okay, so probably not like 2.2, they will be too close to sulfur. Probably not like 6.1, they will be too close to tellurium. If I were you, I don't know the exact value, yeah, but I would probably go for somewhere in between. So maybe 4. They give it to 1 decimal place, so maybe 4.0. I don't know, 4 will be alright as long as it's middle point, right? It could even be 3, it could even be 5. I don't know. It's a suggestion, it's a prediction, yeah? Next up, they want you to work out the physical state of oxygen. So if I have a line diagram that has temperature there, so the melting point the melting point of oxygen is minus 219 degrees Celsius, and then remember that you're dealing with negative region, so this is actually a more positive value than this. This is bigger value than this. So there's melting point, and there's boiling point, and your minus 190 is here. Melting point is when you go from solid to liquid. Boiling point is when you go from liquid to gas. All right. So the oxygen, which exists as O2 molecule, whether it's solid, liquid, or gas, it is still going to be O2 molecule. All right. But it is a liquid at minus 190, and the reason is because it already melts. It melts at minus 219 degrees Celsius. So minus 190 degrees Celsius is above melting point. So it already melts because you already reached the melting point. But minus 190 degrees Celsius, it's still, remember you're dealing with negative region, right? So this is bigger than this, all right? So minus 180 degrees Celsius is still below the boiling point, which is, so you need to use the information, you need to state it, okay? Because here they want you to explain, whereas here you just need to use to suggest, all right? Below the boiling point of which is minus 183 degrees Celsius. So it hasn't boiled yet. So it has not boiled yet. If you haven't boiled yet, you haven't gone into the gas, but you're above your melting point, so you're still a liquid, yeah? Conductivity of group 6 elements. So what can you say? Describe the trend. Very poor, quite good, and good. So what can you say is that the conductivity actually gets better. So the electrical conductivity increases, or the electrical conductivity gets better down the group. Increases, we can say get better at conducting electricity down group 6. But essentially you can see the trend increases. There's the qualitative feel about it here. Next up, there's a trend in the melting point of the elements. Which element does not follow the trend? So which one does not follow the trend, and use the data to explain. Okay, so they want the melting point. So look at the melting point. So from here to here we can see it increase. From here to here we can see increase. From here to here we can see increase. But from here to here we see decrease. So that is your something that doesn't follow the trend. So there's polonium. Polonium doesn't follow the trend. So which element does not follow the trend? Polonium. Okay. So from here all the way to here it increased. Melting point increase. Oxygen to tellurium. From oxygen to tellurium, so you can spell from the table itself. Okay, I know the spelling already. From oxygen to tellurium, the melting point increase. All right, but then it decreases from tellurium to polonium. They want you to use the data in the table to explain your answer. So they say it does not follow the trend. So they're not asking you whether it's the structure or the bonding. There's a different kind of question. What they want here really is, why does it not follow the trend? What makes you say it does not follow the trend? Well, you can compare them. You can see it increase, and then suddenly there's a decrease. So generally it increased, but that decrease there is strange. As a science student, you need to think about what is strange, what is out of ordinary, that kind of thing. Yeah. Now next bit, how the structure in oxygen differs from the structure and bonding in polonium. Okay, what can you say? This is melting point and a boiling point, right? So you can see the boiling point is quite high actually. The melting point is also quite high when you think about this is in degrees Celsius. Room temperature is 25 degrees Celsius. So high melting and boiling point would suggest a giant structure. All right. But you can also think about conductivity as a solid. So this is an element. The conductivity is very good as a solid. So we should be thinking about giant metallic structure, right? because it cannot be giant ionic because it's an element, and it shouldn't be giant molecular because giant molecular does not conduct when it's solid. All right, so we should be looking at, because of this and this and this, we should be looking at a giant metallic structure. And obviously for oxygen, you know it is a simple molecular structure. The worst mistake you can make is metallic. The worst mistake you can say is it has a giant ionic structure, because this is not a compound. Okay, giant ionic structure, you must have a compound. This is an element. So you either stuck with giant molecular or giant metallic. Cannot be giant molecular because it conducts when it's solid. Reminds you of metal, yeah, because of free electrons, free delocalized valence electron. Right? Use the information, so you gotta use. So in fact, I just talked through it, so now I'm gonna write it down here. So oxygen has simple molecular structure. So oxygen has covalent bond between the atoms, but between the oxygen atom, there's something called intermolecular forces, and that is what you break because of the structure. So because of the structure, so melting and boiling oxygen only requires breaking weak intermolecular forces between the molecule. Inter means between, yeah. Okay, but then what about the polonium? So polonium is an element, right? It's an element given in the periodic table. So it's very high melting point and boiling point, suggests a giant structure. Must be giant metallic because can conduct in solid state. Can conduct as a solid. Can conduct what? Can conduct electricity as a solid. You see? Very good, right? It cannot be giant ionic because it's an element, as I mentioned. It cannot be giant molecular because it can conduct electricity as a solid. Okay, therefore high melting point and boiling point. Oh, actually they don't need about a melting point and boiling point, they just want the structure and the bonding. Okay, so must be giant metallic structure, therefore with strong metallic bond. Okay, whereas this one is simple molecular structure but oxygen or covalently bonded. So just want to clarify that I know that it has covalent bond, but melting and boiling only requires breaking the weak intermolecular force. So two kind of forces there, yeah? Okay.